Good morning, class. Today we are going to talk about Stokes' theorem. First thing we want to talk about, again, circulation in 3 dimensions. We were doing circulation with Green's theorem and last chapter. Again, circulation around a point P is described with a vector normal to the plane of circulation, and the length gives the rate of the fluid's rotation. That's called the curl of the field. We talked about the K component of curl when we did Green's theorem. Remember, I had you guys find just the K component of curl at the beginning before we even did Green's theorem, because it's the integral over the K component. That's because Green's theorem was just the XY plane, so the normal vector is always going to be the Z direction or the K direction. Now we're going to be doing 3 dimensions, which means that the normal vector might not just be K, it could have parts with I and J as well, or the X and Y. So the curl vector, again, is the vector of greatest circulation, and to find the curl of that, I'm going to give you just the formula here. By the way, you can pause the video at any time to write down what you need to write down. But notice how the curl is given by this vector, and to get it, it's actually the cross product of just del with the field. It's like taking the gradient of crossing the gradient with the field. So that when you do that, you get these 3 pieces. Again, this piece right here should look familiar because that was the formula for the K component of curl. Well, now we have a formula for the I component of curl and the J component of curl as well, which you'll need all of them for Stokes' theorem. Because again, now we're moving 3D, not everything's going to be perfectly flat like it was with Green's theorem. But the idea is the same. Alright, so hopefully you guys are done. If not, pause and write everything you need to, and then we will keep going. So the first thing just says, what is the curl of this field? Okay, well, if I make this M, N, and P, because those are the 3 letters we use for fields, and I do the formula, the curl of F, if I look above, it's the derivative of P with respect to Y, well, there is no Y there, so that's 0, minus the derivative of N with respect to Z. There is a 4Z there, so that's going to become a 4. So that's the first component. Then with the middle one, it's dm dz. Again, there is no z there for m. Minus dp dx. We look here and we get 2x. And then finally, we're going to do the k component of curl. Sorry. And it's dn dx. Okay, and that would be 0. Minus, and then we have dm dy, which is a -1. So therefore, the curl of this field is -4. This vector represents the curl, -2x, 1. Okay, that's how you find the curl. Alright, so we're going to use that later. Again, that's just the beginning part. Now we're going to talk about what Stokes' theorem is, but again, it's very similar to Green's theorem. It's pretty much Green's theorem in 3D. So again, if you need to pause anytime you need to. Here we are. What is Stokes' theorem? Basically, the circulation of a vector field, F, given that F is M, N, and P, around the boundary of a curve, C, of an oriented surface S, there's a lot of letters I know, in the direction counterclockwise with respect to the surface's unit normal vector N, equals the integral of the curl dotted with N. Remember, this represents the curl, dotted with the normal vector over the surface. That's a lot of words. Basically what that means is our old circulation and work line integrals and circulation integrals can now be turned into surface integrals in 3 dimension. It'll be the integral over the surface of the curl dotted with the normal vector, and then again we have our surface area like differential. So anyway, that is the thing here that we're going to be doing. We're going to be turning everything into this formula here. So pause the screen if you need to write all this down. I'm sure you will. I am not going to waste time with the video because I only get 15 minutes per video. So there are nice diagrams over on the side here to kind of show you that, hey, we dealt only with the K component of curl with Green's theorem because it was only direction that was normal to the circulation. But now, since the circulation's around this surface, around this curve, the surface has a normal that's not just the K. And actually, here's another great thing. So since this vector now has multiple components, we have to deal with the full component of curl, all the components of curl. Okay? Alright, so let's do this for this problem. Example 2, states, let's do both sides of this equation for this hemisphere. So it's a hemisphere that is, and its bounding circle, the curve that it's going around is it's in the xy plane. So technically we're actually going to be doing Green's theorem here in a way, as opposed to Stokes' theorem, but it's the same thing. That's the whole point. Green's theorem is just a shorter version of Stokes' theorem. So let's do the left side first. So the left side doesn't involve that at all. It involves what we knew before. We have to parameterize the curve. We need f in terms of our variables and dr, and then we have to have parameterize this circle. So to parameterize this circle, we're going to say that r is 3 cosine theta, 3 sine theta, and then 0 because it's not moving off of the z-axis. So this is, by the way, the left side. This is this equation. So we're doing the left side first. Okay. So we have r. We need to find dr with respect to t. By the way, t would go... actually, what I should say is that these are t's, but it doesn't really matter. You know, let's make them t's. It really doesn't matter. But we're going to say t goes from 0 to 2 pi. Okay. Because we used t last time, so we'll use t again. But you can use theta. It doesn't matter. We now need to change f into a vector with the components from r of, r right here. So f is now, in the I direction, it's y, which is 3 sine t. And then in the y direction, it's x, and it's negative. So this would be negative 3 cosine t. And then again 0 because we don't have a z component. We also need to find dr because we need to do f dot dr and then integrate over from 0 to 2 pi. So dr with respect to t is negative 3 sine t and 3 cosine t and 0. Okay. So now all we have to do is dot product those. So we get that the circulation of f dot dr is equal to, if we dot these two together, we get the integral from 0 to 2 pi of negative 9 sine squared t minus 9 cosine squared t dt. And to simplify that, you can pull a negative 9 out, and it just becomes an integral from 0 to 2 pi of sine squared plus cosine squared, which is 1, and then just d theta. Well, that just becomes negative 18 pi. So that would be how to do it without using Green's theorem / Stokes' theorem. That's still just how you do it. Again, it's an easy example to show you how to do it. I'm going to make a little line. And we're now going to show you how to do Stokes' theorem from the right side, or the right side formula, which is Stokes' theorem. Okay, so again, we're trying to set up this integral, which is the curl. Again, that represents the curl, dotted with the normal vector, and then d sigma. Okay, so we need to get all our parts. So if you remember correctly, the curl, or I'll just call it the curl, of f is that formula of from the last page, right? So you're first going to do dp dy minus dn dz. Well, if you look at f, where's my f? Dp dy, there is no p, so that's 0. And then there's no z in the other pieces, so it doesn't matter. dn dz will be 0. Then dm dz, again, there's no z, so that's 0. And dp dx, there's no p, so that's 0. Then we are at the k component of curl, which will work here because, again, this is basically a flat one. So we got dn dx, so that's negative 1 because x, or n is this one here. So it becomes negative 1, and then minus, and then it's just 1. So we get that the curl is actually 0, 0, negative 2. So it really only affects the k component of curl. So we have 0, 0, negative 2. Okay, so we've got this piece right now. Let's check off what we have just so we can keep track. We've got this piece. Okay. Now we need to find the normal vector, right? Well, remember, for any surface, it's either, if you're doing parametrized surfaces, it's just the cross product over its magnitude, but we don't have that. So in this case, it's the gradient of f over the magnitude of the gradient of f. That's equal to n. F is always the surface. So if we look back at our hemisphere, that's our surface, we get that the gradient is 2x, 2y, 2z. Again, that's from taking the partial derivatives of this thing here. Then we do the magnitude of that. So if we do the magnitude of this, this is 4x squared plus 4y squared plus 4z squared, the square root. I'm going to simplify that right now. I'm pulling a 4 out. There it is. And then I'm left with the x squared plus y squared plus z squared. For the normal vector, this is defined on the surface as a 9. So that means that the square root of 9 is 3. So we end up with a normal vector of x, y, z over 3. Again, the 2's will cancel with all these. That's where the 2's went. So that square root of 9 just became a 3. So now I have the normal vector. One more thing we need to find is d sigma. D sigma, remember, is the magnitude of f over the absolute value of the gradient of f dot with p. And again, p in this case is 0, 0, 1. So we know the magnitude of the gradient is 6 because it's the 2 times the 3. So we get a 6 up here. And then the gradient of f is this piece. We're going to get just the 2z. So it's 2z dotted with, it's this whole thing dotted with 0, 0, 1. But since it's dotted with 0, 0, 1, we're just going to get 2z. So d sigma is just 3 over z. dA. There should be a dA here too. Okay. So we've got all our pieces now. We've got this piece, we've got this piece. Now let's put it into one formula. So it's the double integral over the surface of, I have a 3 over z times the normal vector, which is this vector here. Oh, we have to do the dot product. I didn't do the dot product. That's what I'm missing. We have to dot this with the curl because that's the formula. The formula is the curl dotted with n. So there's n, there's the curl. If you notice, there's only one component. It's the k component. So we're going to be multiplying these two things together. So we end up with just negative 2z over 3. Then we're multiplying that times d sigma. D sigma is 3 over z dA. Notice how the 3's cancel and the z's cancel. So I end up with the double integral over the surface of negative 2, or I'll just put the negative 2 out here, dA. Well, again, this is now the shadow region of the surface, which is just the circle with a radius of 3, because it's x squared plus y squared equals 9. So this becomes negative 2 times the area of that circle, pi 3 squared, which is negative 18 pi. So this shows that both sides work, okay? So again, you need the 3 pieces. You need the curl, you need the normal, you need d sigma. So that's the third piece. You need to dot these together, which we did. That became this. And then we left that one there. Everything canceled. It was beautiful. So, all right. Anyway, that is the beginning of Stokes' theorem. We will finish Stokes' theorem with the next video. There will be just 2 examples to keep practicing, and then I will be assigning you guys a couple practice problems for home. Hope you guys are doing well, and I will talk to you later.